Recording. We are going to just introduce work and the conservation of energy. Alright, so here you can see that there's an error with the equation. It didn't transfer over correctly with the superscript. So for this one, it is going to be 1/2 k x squared minus x naught squared. Can you guys see that? Oh, it came up fairly nice looking on the board there. Alright, so we have all those in our notes. We're going to use each of these throughout these problems we're going to go through. And again, that's E naught, standing for E initial. Alright, so here's our first application. 1,200 kilogram car is driving down the road at a constant 25 miles per hour. What is its kinetic energy? Do we have enough information to calculate this? Yes, all right. It may help you to start, listing out your givens. What are we given in this problem? And then the speed. Notice it says miles per hour. That is not our standard units. We have to make sure everything is in kilograms, meters, and seconds. The kinetic energy equation is 1/2 mv squared. We have both m and v. This is the simple introductory problem. Plug in, find our final answer. So before we actually plug in and get our answer, we have to convert our 25 miles per hour into meters per second. So we're going to do that down here. How do I cancel out the hours? Make sure that the hours goes on top so they cancel, and we'll get miles per second. We have to cancel out the miles, so miles has to go on the bottom. And you probably don't know this conversion, but it is 1,609 meters in 1 mile. And somebody do that, and what is that answer? 11.17. All right, so again, we need our standard units. That has to go up into our equation here. So we can get rid of this. We don't need, I can't move everything. Shh. And what do we get for our total energy? 74,000. Yeah, I'm going to round up. Okay, so you can see how much energy a car driving down the road is going to have. Right? Big mass, big energy. I am not on pause right now, but... All right, here's the next problem. This is a comparison type of problem. So a baseball is thrown at 100 miles per hour, and the mass of the baseball is small, bless you. What we're asking is, how fast would a person have to run in order to have the same amount of kinetic energy as a 100 mile per hour fastball? Okay.
Can't this just be like proportions?
If you set it up appropriately with the mathematical relationships that describe the motion, yes. Yes, you can. So that would be sticking with all the variables first, instead of solving for one number and plugging it into a different equation. So yeah. All right, so there's the conversion from miles per hour to meters per second, and as a rough estimate, you can see that it's about half. All right, the meters per second from miles per hour will be approximately half the value. Next thing to do is use your kinetic energy equation. For the baseball, So this is for the ball. So you're going to use 1/2 the mass of the ball times the speed of the ball squared. Did anybody get the energy of that baseball?
149.86.
Okay, so I'm going to round that to 150. Okay. So the next part asks, how fast would a person have to run to have that same amount of energy? So what that means is the kinetic energy of the ball actually equals the kinetic energy of the person. So go ahead and set that one up. Okay, so same equation. Just the person's energy is equal to the baseball's energy. Did that show up? Did you guys see the alert pop up? Okay. I think I have to make sure that's off. And what do we get for the speed of the person? 1.9 meters per second. Now, what would that approximately be in miles per hour? If 100 miles per hour was about 50 meters per second, this would be about 4. So that would be about 4 miles per hour. And most of you in here can run 4 miles per hour. This spring has a spring constant of 100 newtons per meter. Now, just if you say that out loud, 100 newtons per meter, what that's telling you is it would take 100 newtons worth of force to stretch that spring 1 meter. But we're going to take that spring, compress it 0.2 meters, and just figure out how much energy is stored in that spring. So what's the spring equation?
1/2K parentheses x2 squared.
All right, so let's write out that long version, 1/2 K x squared minus x naught squared. What would the x naught be in this equation? We're going to have this be 0. Most of the problems you're going to see, it's going to be compressed from a starting relaxed state of 0. Okay, which leaves us just with 1/2 kx squared. No more complicated than the kinetic energy equation. What is the value of the spring potential? Spring potential here is 2 joules. Right? All right, looking at the units, you can see that we have a Newton over a meter times a meter squared. Those cancel out, left with newtons times meters. Equation for potential is we want potential energy. mgh. So remember, height is what really affects the energy of the object. What would the mass be that I have to use? Has to be in kilograms. 0.01 kilograms. G is just 9.8. H is 2 meters. So what's that value? 0.196 joules. Okay. All right, good. All we did was use the equations for each form of mechanical energy that we know. That's as basic as a problem we can do. Now we're going to throw that word work into this.
Sure you want to do that?
I'm sure. I think this is a good idea. Okay. So before we actually really start talking about work, so how did that monkey gain its energy?
Put it up. Increasing the height.
So increasing the height.
Its mass.
The mass wouldn't have changed. All right, we got to it. Energy had to be used by a person, and that person had to exert a force. In order for that monkey to gain its energy to be raised up to that flagpole, a force had to be applied. If there was no applied force, there would have been no change in energy. So what's the answer to the next question? How does any object gain or lose energy? All right, so any object gains or loses energy by an applied force. So this object gained its energy by an applied force. So any object that gains or loses energy has to do so through an applied force. Simple?
So let's say Paul.
All right, now you have this paper in front of you for the introduction to work. I went through a brief statement of this, and we're recording right now. So all of you are on video for the whole world to hear. Okay? So let's highlight a few things here. The simplest form of the definition is a change in energy. If you hear the word work in physics, besides me saying do your work, it is a change in energy. What they're going to test you on is, for understanding that definition, is they will ask you for what is the work done, but you will have to go about finding that from the change in energy. And then they'll ask you a question is, what is the change in energy in this situation? And you'll have to find it by the work equation. So they're going to flip those two, just to check that you understand what the definitions are. And we just answered this, that all of these changes in energy occur from the application of a force and a displacement. The object will have to change its position in order for there to be that change in energy. All right? This is the way you want to think about work, is that the work is done by a force that acts parallel to the displacement. So in that other equation we had where we had the cosine function in there, that's just solving for that x component. It'll be the part of the force that is going to be parallel. That's all it's standing for. And we get that from this drawing here. If we just use this drawing, you can see that the angle given in that location, if we use the cosine, we would find just the x component of that force, and that is parallel, pointing in the same direction, or along the same plane as the displacement. They might not always give you that angle. So you either have to find that angle, which we defined as the angle in between the force and displacement, hence it's right here in between the force and the displacement. But depending on how the problem is drawn out for you, you can use the sine function as long as it's solving for the component that is parallel along the same direction as the displacement. So think about it more like that. Make sure that that's your understanding. You need to have the amount of force that is in the same direction as the direction of motion. Or, I'm sorry, same plane of direction, because it can go opposite the direction of motion as well. Are we okay with that? So I'm not going to read through this with you. So that's just now moving my writing here. We mentioned the other day that when there is no angle, right, we will get the maximum amount of work being done. Okay. Anytime there's an angle, it changes how much force is parallel, so it'll always be less than its max whenever they're pointing in the same direction. So let's look at the way this question is worded. So suppose the monkey fell from the flagpole. How much work did gravity do on the monkey? So notice it's asking for work. It's mentioning a force. All right, what would we do in order to answer this question? So one way to go is work is equal to force times distance, the work equation. The force you mentioned is mg, the weight. And then the distance that you mentioned was the 2 meters, which would be, another word for that type of distance is the height. Right? So look at that equation. What is that the equation for? Potential energy. What type of energy is changing if that monkey falls? It's going from, what type of energy does it start with? Okay, and then changes to something else, right? But it's the potential that goes from something to nothing. So the work done by gravity to change that energy from one form to another is just going to be equal to that value of mgh that it had, because it's going to lose all of that. And you can see that it works out if we do the force times the distance equation. The force that's acting, the only thing acting on it would be gravity when it's falling, and the distance it would fall is the height that it's at. So really, the work done is equal to the change in gravitational potential energy, which we had that number as 0.196 joules. I said it wrong that time. So the next question is, how much work did I have to do to put the monkey up there? That's supposed to be a J. So the work done by me would be 0.196 joules. Okay, the force I would have to exert is at least on average equal to mg, and I would have to raise it the height of 2 meters. All right, so there the energy gained by the object is equal to the work done. So I would be putting energy into that system. All right. So now, work done by friction. Friction will remove energy from the system. All right, so it's removing the mechanical energy. It's changing it from a mechanical form to a thermal energy. All right, so it's no longer mechanical, won't cause motion of the object. So yes, work can be negative. In the instance where we looked at a book sliding across the surface, right, without anything else acting on it, just as it's already in motion, the direction of motion was one way, okay, but the friction would have to act opposite. So in our work equation, our force would be the friction, and that's going to act in the negative direction, while the displacement is to the right, which is positive. Almost every single problem, and I only want to say almost because I don't like always statements, we have our friction on a flat surface. So because it'll be on a flat surface, that means that our normal force from our fun equation will always equal mg. Okay, so this substitution from FD to mu mg is just from that fun equation. So if you see the mu, you have to pull that friction equation into your toolbox to find that answer to that problem. So when energy is conserved, the amount that we start with has to equal the amount that we end with. However, if there is friction acting, that is going to remove mechanical energy from that system. So that means that will always be true with friction. The total mechanical we start with will always be greater than the total mechanical we end with. In order to make that an equality, we either have to add to one side or subtract from the other side so that the numbers match up. All right? I tend to write it out this way. Because I know that this is the bigger number, I'm going to add how much energy is lost to the other side. If I start off with 10 joules and end up with 6 joules, I know that 4 joules was lost due to friction. If you don't like that, you can just write it this way. Subtract the FD onto over to the other side. Since this number is larger, if this is 10 joules and this is 6 joules, I would have to subtract 4 from the 10 side to make it equal the other. So if this makes more sense to you, start out your problems that way. This is an always statement. Just like in circular motion, where the sum of all the forces equaled ma for the centripetal acceleration, that was always. It always was applied. Bless you. This is an always statement. If there is no friction, then energy is conserved, mechanical energy is conserved, and it's just that statement. Okay? You would just have to know that this thing right there is 0. Okay? So that's really an always statement. You can always start your problem that way. If you ever get in any trouble starting a problem, you write that down. Because it's correct. All right, let's try one of these that are at the bottom of your paper. We're going to start with number 1. I would say this is really not an introductory problem, but we can handle it. All right. So we have a block against the spring, and it was originally at rest there. So if there was no force applied to that block, this would be its 0 relaxed state. What's happening here is once this spring decompresses, it'll launch the block and it'll slide along a surface and come to rest in 6.8 meters, which is a very long distance. Okay. So at this point, the block has no speed. Mass of the block is 3.9 kilograms. The spring constant is 640 newtons per meter. Again, takes 640 newtons to stretch that spring a meter. And the mu at this point, as it's sliding, is 0.25. All right, now A asks for the increase in thermal kinetic energy, so just in the heat, and B is maximum kinetic, and C is original compression distance of the spring. So that original compression distance would be how far back we push the block from its resting state. So we read the first one, what is the kinetic, thermal energy created? You might not have any idea of how to specifically solve for that. On the previous page, I said there's an always statement. This can always get you started with any type of problem, which is the initial energy has to equal the final energy plus any work done. And in this case, it would be the work done by friction. Now, this is the thermal kinetic energy. That's the heat. So I don't even know what I'm going to be able to solve for yet. I'm just starting with this statement and going to go through a process, and we'll see where it ends up. All right. At the beginning, I am looking at whenever the block is pressed against the spring. I see that there is a spring, so there is a spring potential. It doesn't have a height, so there's no gravitational, and it's not moving, so there's no kinetic. So the only starting energy that we have is 1/2 k x squared. And at the end, the block has slid to a stop, so there's no kinetic. Does it have a height? No height, no gravitational potential, and there's no spring at the end. So really, there is zero mechanical energy at the end. But that's impossible. This left side of the equation has to equal what's on the right-hand side. The only thing left is that work due to friction or thermal energy. So, well, right here we have a statement. Do we know K? Yes, we do. Do we know X? No, we do not. Okay. Well, work done by friction is going to be the frictional force times the displacement. Do I know the frictional force? No. But I do have a mu. So I'm going to substitute in mu. It's a flat surface, so the normal force is G. And then I do know D. And that equals 1/2 k x squared. Let's look at what we know. Okay, so I know D is 6.8. I know G. I know the mass of the block. And I know mu. Well, right there, if we just think about what all of that is on that side of the equation, that is the thermal energy. So it really, at this point, we can solve for part A, because that thermal energy due to friction is mu mg d. We can actually get that number. What else we can do at this point, since we know everything? We know everything on the right-hand side. On the left-hand side, we know K. The only thing we don't know is that X. So at this point, we can solve for X. So from starting with this process, we can solve for both A and C just from going through that work. All right. This one is actually a little bit more obvious to solve for. This it requires a little bit of understanding of what this part means in terms of the thermal energy. All right, so on this side, we're just going to use the μmg so that the thermal energy is equal to 0.25 times 3.9 times 6.8 times G. Squeeze that in there. Right there. If we plug that in, you'll get 64.97, so rounds up to 65 joules. We're going to skip part B, and let's move over to solving for part C, which is that X, that compression distance. So we're just going to manipulate over here for X. So mu mgd stays on that side. We're going to multiply both sides by 2. Then we're going to divide by K. And then we have to square root everything. So now, if we plug in all those values, we will get the 0.45 meters. And if you see it a little different, so if you went this route, that's how you would do it. If you solved for this part first, what we could have done, which would make it look a little bit more simple, is since we know that mu mgd is 65, all right, you can just plug in that number for the mu mgd. You get the same answer. Okay. All right, so we found X. So point C, or part C is 0.45. We found A, which is 65. Now, if we look, the maximum kinetic energy of the block, so that would be when the block is moving its fastest, has the same amount of energy as the 65, right? Well, that goes back to our original statement. Right here, okay? So in the beginning, we just had spring potential. Here we had 0, and there we had the thermal. So this is the maximum amount of heat that will be generated. That has to be equal to the maximum amount of spring potential that we could have. As soon as that spring starts to decompress, the spring energy goes down. However, the kinetic energy will go up. Once the block is no longer in contact with the spring, all right, when we ask ourselves, is there a spring, we have to say no. Okay, is it moving? Yes. If it's moving before it hits that frictional point, okay, then there is no thermal energy being created either. So, the maximum energy that anything could have is when it is the only form of energy that exists at that point in time. So at the beginning, only form of energy, spring energy. When it's moving without touching the spring or the rough surface, maximum kinetic. When it's stopped completely, there is no more motion, no mechanical energy. All of that energy has to be heat, and it'll always have to be the same value. All right, so after solving that problem, we wanted to be able to explain why an object that is sliding along a surface comes to a stop, but using energy. So the simple statement is that the surface and block friction is going to generate heat. That heat is going to remove the mechanical energy from the system. Once the object stops, all right, the only energy left is the work done by the friction, right? So at first, this object would be moving. At the end, there is no mechanical energy. The only thing left is the work done by friction, which is no longer mechanical energy. There is no motion, okay? So there is no energy. So why does it stop? All of the mechanical energy is removed, so therefore it cannot no longer have kinetic energy. It has all been taken out of the system in the form of heat. All right, so this is a problem we actually did. I think it was the first one that we did. So 1,200 kilogram car traveling at 25 miles per hour, and it comes to a stop. So we originally found the kinetic energy of this car. We converted the units from 25 miles per hour to a speed of 11.17 meters per second. All right. It's asking for what is the work done on the car. Again, starting with this statement. If it starts with kinetic, stops, meaning that is zero, there's no more mechanical energy, the energy had to all be generated into heat. Okay? We found this. We found that in our first problem. We found the kinetic energy of our car to be 749,000 joules. So the work done on the car was equal to the kinetic energy that it had. The work done, though, just happened to be negative because it took the energy away from the system. Then it just asks, what is the force that does the work on the car? Well, it's going to be the work done by a frictional force. If we wanted to calculate that, we would have to know the distance that the car is sliding. And we can just figure out what the frictional force was. We can even take that steps further and figure out what the coefficient of friction is between the surfaces. Right, but it's just another way that they're going to test you on understanding what is the definition of work. So in this case, it's the change in the kinetic energy, because if this was all kinetic, here the kinetic was zero, that change in kinetic energy is equal to the work done. All right, so here's one more example problem. It's a bullet that is shot, and it stops as it enters a clay block. All right, first part is asking what is the work done to stop the bullet. what is the change in energy? The energy that's changing here, it has kinetic at the start, it has no energy at the end, so where did it all go? So the starting energy is kinetic. There is no more mechanical energy. We're imagining that the bullet starts at one location, flies in a straight line path, and enters the wall and stops. So that all of the energy must have been removed by the force, and we'll just say it's a resistance force, the frictional force. So the work done would simply be equal to the change in kinetic energy, all right? Where the change in kinetic is going to be the final, which is 0 minus 1/2 mv squared. So in this situation, if you write it out that way, you can get the negative out of it. Now the hard part is figuring out the value of the force. Okay, so we know the work done, and we're looking for force. We need to know the distance. Okay, the work is 30. The force is what we want. Distance, not there. Right? They give us time instead. All right, so we have time, and it says 600 microseconds, but I tell you that a micro is times 10 to the negative 6th. We know that the initial speed is 200. We know that the final speed is 0. And we are looking for distance. So we go back to our kinematics. Pick the correct equation. All right, we'll plug in our numbers, and you should get 0.06 meters. Once you have that, that just goes right into your work equation, so that force is equal to the work done over the distance, 30 joules divided by 0.6 meters, gives you a force of 500 newtons. So this doesn't go away. Chapter 1, right? All right, so that's the introduction to work and some basic conservation of energy. You'll get more practice, and plus these problems are going to be more focused on the conservation of energy, and look at some other aspects of work when it comes to graphing and springs. So we'll come up with another video for the next section.